Okay, so what is a normalized function? Yeah, well, um, I might as well show it to you from the second problem, since second problem is already a homework, right? So what's the second Legendre polynomial? P2 of x is 1 half 3x squared minus 1. Okay, and let's say I want to find the norm of this on minus 1, 1. Well, like I indicated, the norm is just the square root of the integral from minus 1 to 1 of p2 of x squared dx. And so let's do that. So minus 1 to 1, let's square p2 of x. So that's 1/4. Let's leave it outside. 3x squared minus 1 squared. So this technically was 1 half squared to find the norm. I'll find the norm squared and then square root it. So, and if I do that, I will get 1/4. Let's open this up. So 3x4 minus 6x squared plus 1 dx. From minus 1 to 1. Okay, well, 1 by 1, basic integration. 3x5 over 5 minus 3 over 3, 2x cubed plus x from minus 1 to 1. And then if we evaluate this, we will get 1/4, 3/5 minus 2 plus 1, that's for 1, minus 1 will get us minus 3/5 plus 2 minus 1. Okay, and then if we simplify this, we get 3/5 and 3/5, that's 6/5. Minus 2 and minus 2, that's minus 4. Plus 1 and plus 1 is plus 2. So what does this add up to? 6/5 minus 2. What is that? That's just this will get us 10 over 2, so minus 4/5. So 1/4 minus 4/5. 1/4 minus 4/5 is times minus 4/5 will get us wait, we have a negative answer here. Something can't be right. We can't have a negative answer. Let's see. Oops, yeah, this is 9 because we squared it. 9, that puts a 9 here, which makes this a 9. Which makes this a 9. 1/4, yeah, which makes this 9 and 9, 10. So this is a 2. Wait, I'm still getting a negative answer. Minus minus 2. No, I'm getting 0 now. Oh, 18 fifths, 18 fifths. So this is 18 fifths minus 2. This is just 8 fifths times 1/4 will get us 2 fifths. Yeah. So 2 fifths. Now it makes sense. It's a positive answer. So this is n squared. So that tells me that the normalization is just 2 square root of 5. Square root of 2 over 5. So this is the normalization, yeah? This is the norm of the function. Okay, let's do a bit of discussion on the normalized function, because the application of that is manifest in physics. Yeah. So as it turns out, when you take, let's say, okay, let me discuss here a little bit the normalized function. You're there, Ben? Normalized function. So so let's say when you normalize, when you try to normalize sine nx, on 0 pi, you go and integrate 0 to pi sine squared nx dx. And if you do that, we did this problem before. The answer was pi over 2. So that means the norm for this function here, if this was, let's say, f, the norm of f, right, is square root pi over 2, because that's what we got there, square root pi over 2. Okay, now what we say is, we say that the function 2 over pi, because what does normalized function mean? It's like unit vectors. When you take the unit vector, you get 1. Like say I dot I, you get 1. Yeah. The same thing applies in functions. So when you take the reciprocal of the normalized function, in other words, n to the minus 1, multiplied by sine nx, you're supposed to get 1. That's the whole idea behind normalization. Okay. So this has a norm of 1 on 0 pi, because we've already proved that this guy here has a norm of square root pi over 2. So if you multiply it by its reciprocal, you will indeed get 1. So what is it that gives you a multiplicative factor of 1? That's the point. Now, why is this important? Because there's a theorem that says a set of normalized orthogonal functions are orthonormal. Okay? A set of normalized orthogonal functions are orthonormal. They have to be orthogonal and they have to be normalized. That's what orthonormal means. Orthonormal. Okay. This here is an essential feature of these functions. Okay. Okay. This is sort of talking about I, j, and k, the basis unit vectors, which are orthonormal functions, meaning you could take any vector in 3D and you can express it. So if you take vector A, right, since in 3D, in R3, since I, j, and k are orthonormal functions, you could take any vector and express it as components, one along the I, another along the j, and another along the k. And the reason you are able to do that is because I, j, and k are orthonormal functions in R3. These are unit vectors, and they're orthogonal, and they have a norm of 1. Okay, so you can juxtapose this, right, on functions. So if the elements of your vector space are functions, then you can use the orthonormal sets of functions or subsets of these functions as the basis vector of the space. Okay, so an example on that. When we expanded f of x back in a Fourier series, yeah, we said f of x is the summation of, say, coefficients Cn, right? And let's say that we do the Fourier sine series or cosine, either way. This was 2 over pi, because we know that's the normalized function. We just said that, sine nx. Okay. What we're saying is we're indirectly saying that f of x is some kind of vector that has components c1, c2, c3, ... till cn in terms of the basis vectors, like the ijk in R3, in terms of the basis vectors of root 2 over pi sine nx. So that function is serving as your ijk in R3. There you have 3 components. Here you have n components, and the c's are acting like the value of these components along every direction. Okay. So this is an example of that. And you know, the relevance in quantum mechanics to a function that, say, represents the state of a physical system, they call it a state function or a state vector, because of everything we've been saying here, for the reasons we've been discussing. Okay, so just like you could take any 3D vector, a 3-dimensional vector, and write it in terms of I, j, and k, because those basis functions, standard basis functions, are orthonormal in R3. You could also, you know, do it in spherical coordinates or cylindrical coordinates, whatever, right? You could, by the same exact analogy, you can expand f of x in terms of any orthonormal set of functions, and find the components of this new function relative to the new basis set that you choose. So to conclude, so this was, you know, sort of like the qualitative discussion of the matter, but to conclude, if we go back to the question, what is the basis function for what were we doing, the P2 of x? So that would be the reciprocal of whatever we got, so square root 5 over 2. So the answer to our question, normalized function, was the reciprocal of what we got, square root 5 over 2 times the second degree Legendre polynomial. Okay, this is the normalized function of the problem we were just doing. Questions so far?